take a minute and talk about cyclohexane. And cyclohexane it's a little bit larger, of course, than cyclopentane, and it can adopt various conformations. So first, if we take a look here at the simplest one, and this is how I want to start this, I want to take a look at what you would have here if you took cyclohexane. So here's our, that's our flat cyclohexane. So remember, as we draw this out flat like this, each one of these carbons has an H on it that's on a wedge and on a dash. So going around this ring, H's coming out at us and an H going back. So let's put those in. And I want to show you what this would look like if we just had a flat molecule of cyclohexane. So let's take a look and see what that looks like. So here is our flat molecule of cyclohexane. Now if we take it though and rotate it on its side here, you can see what we were just trying to indicate, right? All of those H's that we have on wedges are going to be on the top kind of side of this plate, right? All of the H's that are dashes are going to be on the back. And now as we look around these carbon-carbon bonds, if we look down this bond right here, right? There's a carbon in back. This is the carbon that's in the front right here. If we rotate that around, we're eclipsed. In fact, as we move all around this, every carbon has H's that are eclipsed with each other. So this is a pretty horrible conformation because we have eclipsed H's along every carbon-carbon bond. So one of the things that we're going to start off doing here to alleviate some of that is we're going to imagine that we take that flat molecule and we're going to take one end of it and we're going to pull it up. And that's going to give us something that looks kind of like a chair, right? So you can imagine perhaps there's a person sitting in the chair right here, right? Body bent over, kind of like that, right? So there's a person, right, studying OChem in their chair. So we call this the half chair. So let's take a look at what the half chair looks like. So this is what that is going to look like. Remember, before we had this planar cyclohexane. We're going to take the carbon here at the end and we're going to pull it up. And so that's kind of what our chair looks like, right? So this is like the seat of it, and this is your back. Now as we look down this carbon and this carbon bond, we can still see that we're eclipsed there, right? So we're eclipsed there, and then if we keep rotating around, those are eclipsed with each other too, right? And on this side also, these H's are eclipsed. So going around the ring, right now we have 1, 2, 3, 4, and this guy over here, 5 times 2, we have 10 H's that are eclipsed. What about this? What did that accomplish? Well, let's take a look. So I want to look down this carbon-carbon bond right now. So as we rotate around and we come and look down, we can see that that looks like it's pretty much staggered there, right? As we come around and look on this side, looking down that carbon-carbon bond, we're pretty much staggered there too. So by pulling that carbon up at the top, we've avoided having eclipsed H's, at least at one of the positions there. Right, so as we go through and look at this, and we want to try to get good with this, and you might need to build a model for this, but all of these atoms that are kind of darker up here, right, all of these guys, these are all eclipsed with each other. Okay, all of those H's are. Okay, now down here at the bottom, and this one should be dark here too, by the way, this guy right there. It's on the top. And on the bottom, all these kind of clear are white little hydrogens. Those are eclipsed with each other too. So 5 carbons have 10 H atoms that are eclipsed. That's 5 times 2. That gives us 10 hydrogen atoms that are eclipsed. And along this bond right here, we turn out to be somewhat staggered there. Okay, so that is called the half chair. It's not that stable. It's more stable than a flat cyclohexane though. Now the next conformation is called the boat conformation. So the boat conformation is going to take this same flat structure, except what we're going to do is we're going to pull up that side like we did with the half chair, and we're going to pull up this side right here. And in essence, what we're making is something that looks kind of like a boat, right? So it's like a little origami boat. And when that happens, you'll pull up this end, of course, and this end, and those H's are going to move as we pull them up. And the interaction here between these H's that are pointing in towards each other are called flagpole interactions. They're flagpole atoms that are there. All right, so I want to show you that. Let's take a look at that. And then what we're going to do is we're going to try to take a look at this thing as a Newman projection. It's kind of tricky, but we'll look at the little JMO picture to help us out with that. So let's take a look here. Now here is our boat. So you can see we took both ends and pointed them up, and that puts these H atoms kind of pointing up right now. Now as we look down this carbon here and this carbon here, as we look down those bonds, what you can see is that we are eclipsed there, right? So the H's that are off of the carbon that's here in the front and the back are eclipsed with each other, and the H's on this side are also eclipsed with each other. But look, we have 1, 2, 3, 4, 5, 6, 7, 8. So this has 8 eclipsed H's. So it's better than the half chair, which had 10. Right now, if we rotate this around, this interaction right here, these interactions, that is what we call that flagpole interaction. Now, as far as the Newman projection of this, what I just showed you guys before was something that kind of looked like this, right? So let's take a look at that again. If we rotate this around here, this is what we're trying to draw for our Newman projection. Right, let's straighten it up a little bit. So what you have is a carbon in the front, that's your dot, and then a big circle in the back, right? And then a carbon in the front and a carbon in the back. And then off of that you have here a CH2, and then in the back you have another CH2. So when you put that all together, you end up getting a conformation that kind of looks like this, right? So 8 hydrogens being eclipsed there. Now, one of the things that we can do is we can take the boat, I should say. Now, one of the things that we can do is we can take that boat, and if we grab this atom and this atom of our boat, and this atom, and give them a twist, twist them in opposite direction, we get something called the twist boat. So this is what the twist boat looks like. It's kind of a mess. But when you look at it here, you can see these are the carbons that would be like the bottom part of your boat, and then these ends would be the front and the back part of your boat. And what you're getting here is a twist. So the end result of that twist is this. Remember that these H's on these two carbons, those were eclipsed with each other in the boat conformation. So as we rotate this around, check it out. They become slightly staggered with each other, right? So we're staggered here, and we're slightly, it's not perfect, but we're definitely not totally eclipsed right there, right? We're not eclipsed anymore, so we're staggered. So that has a lower energy. We've lowered the energy of the molecule by reducing the number of eclipsed hydrogens. But we still have these flagpole interactions. So if those atoms are H's, not such a big deal. If they're big groups like methyls, or what if they're tert-butyls, then there's a lot of steric repulsion there. We'll talk about how to deal with that as we get into substituted cyclohexanes. Right now, the one that you really need to make sure that you know how to draw is called the chair conformation. So the chair conformation has no eclipsing, right? Up here with our twist boat, lower in energy, not really any eclipsing, but flagpole interactions is a problem. Here we adopt the most stable conformation. So we're going to pull up one end, and that would have given us the half chair. But rather than pulling up to get the boat on this side, we're going to pull it down. We're going to come down, right? And that'll give us the chair. So without our H's, it kind of looks like this. This is the full chair. So now you have a headrest. This is where the body is, and down here is where your legs would go. Right, so it's kind of like your chair. And when you do that, it changes the position of our H's that are on these carbons. So as we pull this end up here, it's going to put one of our H's pointing in this top position. And as we push this end down, the H that's pointing down comes down and it sits down here just like this. Now, what that looks like is pretty interesting when we take a look at the actual structure. So without the H's, this is kind of what that looks like, right? Like we've pulled up one end and we've pushed down the other end. Now the H's matter, so let's put those in. So with our H atoms in there, we could see as we pulled this end part on the right-hand side up, that H points directly up, and the other H, as we pull that end down, points down. So drawing this thing is actually a skill set. It's a little bit of an artistic thing that we're going to have to learn how to do. But there's an interesting pattern here. So in this particular chair, as we pull that carbon up, if we can just remember that that H points up, then we know where all of the H's are for the rest of the molecule. So that goes up. Now look, the carbon that we're next to, that H goes down. The next H here comes up. The next H comes down, up over here, and then down over here. All of those positions are positions that we call axial positions. And then what we want to do is we want to put H's in at the equatorial position. And if you look at this carbon right here, our goal is to draw things that look like tetrahedrals. Right? So look, we have a H coming down to a carbon. That looks like just a beautiful tetrahedral. So that H that's coming off of here is going to turn out to be parallel with the line that's one carbon behind. So that line right there and this line should be roughly parallel to each other. All right. And as we go back and look at this H here, that H should be essentially parallel with the one carbon behind us, this. If we come over here and look at this bond, that bond right there should be parallel with this bond, right? And then this bond here, going one carbon back, parallel with that bond, so on and so forth. And we'll practice doing that a little bit. Now, this is our chair conformation. Let's take a look. As we go through, look at that. That's perfectly staggered right there. Coming down at the next bond, staggered down this line right here. In fact, this is a very nice way to end looking at our Newman projection. So these carbons are going to be in front. We're going to draw a big circle, right? And then a dot. So the dot would be on the front, circle would be on the back. Little dot here, big circle on the back. And then we're going to come up to a CH2, right, on the front. And on the back side, we're going to come down to a CH2. So let's look at that. That's what this is going to look like. So as we go through here and put in all of our H's, so this carbon that's right here, that is this position right here. And we don't typically draw out the C's and the H's. Right? This carbon is the little one that's in the front. That's this position right here. That carbon right here is the little one that's in the front right there. Right? And they're connected to that CH2 that's up here in the front. They're connected to this guy, right? And then behind, we have this carbon and this carbon. That's this big circle. Those are the carbons that are behind, right? And then sticking off of that, we have another CH2, but that CH2 should be pointing down, and that's right here. Now, we're locked into this kind of Mercedes-looking symbol here. And once we have those CH2s in, the blue ones that I've just circled, all the other positions fall into place because we want to draw an angle of 120 degrees between each one of these positions, right? And that's how we would draw our Newman projection of this. Now, with all of this, we need to learn how to put all that together. So the question is, we've got this half chair, we've got this boat conformation, we've got this twist boat, we've got this chair conformation. They all differ in energy. Notice that the chair has no eclipsed H's, so it would make sense that that might be the lowest energy. So if we look down here below, here's a nice little picture of our energy profile of cyclohexane. So we're starting off over here, right? Here's our chair conformation. With the chair conformation, we have 0 eclipsed H's. So low energy, right? So coming up from that, if we just follow along right here, we're pulling up right here, we're coming up here, that is our half chair. Our half chair, we said, has 10 H's that are eclipsed. Now, as we get from our half chair, that's where we just, our first kind of transition is, we're going to pull up this end. Eventually, that'll lead us to the boat, but as that pulls up, we get a natural twist on these positions so that we next hit the twist boat. Now, that twist boat is the situation, remember, where we have no eclipsed H's but flagpole, right? And then to get from one twist boat to the other twist boat, we have to go through the full boat conformation. Right? The boat conformation has 8 eclipsed H's. And then we twist kind of the other side, and we get the other twist boat. Right? And then pulling this back up, if we keep moving this direction, what we're going to do then is we take this end and we pull it down. Right? So that'll get pushed down. There's your other half chair. And then we fully take that and go all the way down to get the chair. Now, these two chairs are actually different from each other, because notice here that that carbon number 1 is carbon number 1 right here. Right, so that's 1, 2, 3, 4, 5, and 6. This is important. Those carbon numbers don't change. Right, so number 4 is up high on our boat. Number 1 is up high here. Right, and that's 2, that's 3. Right, 4, 5, and 6. And then up here, we still have that as number 1. And our number 4 now is kind of coming down, right? And of course, there's 2, 3, 5, and 6. And then over here, our number 1 is at this position, and our number 4 is down here. That's 2, 3, 5, and 6. Right, so in essence, what you've done is you've taken this 1 and pulled it up, and this 4 and pushed it down. And this situation is called a chair-chair interconversion. So we need to know how to go back and forth between these two. And that's one of the things that we're going to learn in the next section.